All right, bro, if you're an electrical engineering student and you're daunted by the amount of components there are and data sheets for these components, well, I'm just going to start creating videos going through data sheets. And so you can get a feel for how you can quickly just go through a data sheet and maybe you can learn some things along the way. So this is for an analog to digital converter, 12 bits, and it comes in different variations, so you could get it in different speeds, powered from 1.8 volts analog and 1.8 to 3.3 volts on the digital. So we have two supplies that we need to give to this chip to get it up and working. Now, generally speaking, your analog supply, you want to keep it ultra, ultra, ultra low noise. Your digital supply, you want to keep it ultra low noise. And we could use LDOs for that. And we'll go through LDO datasheets one day. SNR, this just tells you how your noise compares to your signal. Essentially tells you your signal to noise ratio. That's literally what it means. It's like, is my signal ever going to be buried in the noise? You look at this number and you can compute some things with it. This tells you how much power you're burning. Of course, with higher sampling rates, you're going to be burning more power if you get that variation. If you get the 20 megasample per second guy, you burn just 45 milliwatts. Now, we could go into theory of megasample per second, but that's just too much. We're just going to go through the datasheet. Differential input bandwidth, 700 megahertz. So you could give a signal up to 700 megahertz and it won't be attenuated that badly. That's what this tells you. But yeah, that's for more advanced signal processing things when, okay, let's just keep going. On chip voltage reference, which is nice to have, usually an external reference is better for temperature compensation and other compensation needs, but this is probably good enough. This tells you your full scale input, so minus 1 volt to 1 volt, because 2 volt peak to peak is your full scale input. I don't know, I don't feel comfortable talking about this because I don't really understand it so much, but I think it has to do with resolution, noise, and just your minimum detectable signal that you can confidently get. Uh, Now these are just cool features. So we have built-in selectable digital test pattern generation. We got a clock divider. We got some ways to format your data, energy saving mode, and data clock out. This is good for actually taking your bits out to an FPGA or a processor and like correctly latching them on the good clock edges. Here we see a bunch of applications. We're going to be mostly analyzing this from a communications and radio system point of view, so using this as an IF analog to digital converter. So, okay, we see our SPI lines to get into the internal registers to set up the chip, actual digital bits coming out. These are all to pin strap the device to get into just basic configuration. Then we go into the SPI and actually program it. You actually feed your signal in here, reference, sense, and clock. Okay, so clock and VN need to be ultra conditioned. So let me say again. Your voltage input and the clock need to be ultra conditioned to correctly use an ADC at high speeds. Or just generally, your clock and how your voltage input are conditioned really, 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 really matter. So yeah, table of contents, general description, blah, blah, blah. Okay, now we don't like to look at numbers right away because if we just take, like we just looked at the front page and we already have a general description. Okay, what do we need to supply our voltage? Does it have enough SNR for what we need? Is it gonna take too much power? This is the minimum we need to be like, all right, am I gonna look deeper? And when I say I'm gonna look deeper, I'm not gonna come here. I'm not gonna come and look at this because that's too deep. I need to go slightly deeper, not like all the way like straight into the nitty gritty. Well, what I would first do is actually come here and look at the FFT that these guys claim that you can get. See, like, oh, what are these spurious tones? Ah, nasty, but I don't really care. I see minus 110 on the noise floor. Cool, that's pretty nice. Okay, then the next thing I would do is just come and look for schematics and how to set up the chip. So, oh, look, they have how to set up your input. Perfect. Just quickly skimming through this. Ah, look, For baseband below 10 megahertz, that's probably where I would use it. Uh, Differential transformer coupling is recommended. Boom. We have resistor capacitor, and we see from 0 to 70 megahertz, I'm going to use it under 10 megahertz. So let's put a 33 and a 22. Boom, done. And then we have to put our common mode voltage center tapped into our balance. So, okay, we know how to set it up. And our input voltage reference. So a stable 1 volt reference is inside. And if you look at table 10, if sense is grounded, we use internal. So, okay, that's done. Clocking. This is very important. You need ultra low jitter because if you have high jitter, you're just gonna ruin everything. Like actually, like the clock is extraordinarily important. You can't just feed any clock. You gotta condition your clock, and it has to have ultra low jitter. And I really mean that. If it doesn't have ultra low jitter, and you wonder why your SNR is bad, that is why. So I'm gonna be clocking at 20 megasample per second. Probably I'll use a 20 megasample per second guy. So okay, boom, done. We're gonna go with this. These diodes here to clip the clock to save the ADC input. And so this is really acting like a TVS, two Zeners back to back. So like 0.7, 0.8 volts, anything higher than that cannot get into the clocks. That's what this is here for. This is DC coupling. Uh, yeah. I mean, it's already DC coupled, but yeah, I guess it's just there. Yeah. I'm just over analyzing this. Okay. And if I were to use a PLL, I mean, okay, look, I would use this setup if I'm using a TCXO from a crystal. If I'm using a PLL, because TCXO gives you a fixed uh, clock. Or if you use a VC TCXO, you can voltage controlled temperature compensate a crystal oscillator. You can change your sampling rate. But if you're using a PLL, that's like SPI controlled and you want to control it from a Raspberry Pi and change your sampling rate like that. Or like a microcontroller wants to change the sampling rate. I'd use a PLL and then that's a whole different chip. And then that chip would feed into a PECL driver or LVDS driver. And then you feed that into your ADC. And there's input clock divider, clock duty cycle. So 50% duty cycle, okay, pretty whatever. Okay, jitter, look at this. Look at the constraints on jitter for 1 second here, right? Each of these colors represent different jitter. If I have 1 picosecond jitter, bro, 1 picosecond is a very small amount, and my input frequency is 20 megahertz, I'm gonna get like 73, 74 SNR. But look at that. If my input frequency was 80 megahertz, if I'm using that 80 megasample guy, oh my god, it's just taking a hit. And if you have worse jitter, we need jitter in the femtoseconds, like 500 femtosecond. We need this type of jitter. Uh, yeah, you need femtosecond level jitter. If you're under 10 megahertz, I mean it's okay. Yeah. But if you're over 10 megahertz, for sure, you're gonna have to go under 1 picosecond of jitter. It comes from this famous equation here. Um, and this is all for the embedded engineers. And normally, this is what a hardware programmer would look at and do their stuff with. I would probably just take this into ChatGPT and tell it to write a Python bit banging SPI code to just get it set up. That's how I would just quickly do it because I like circuits and not programming. So yeah, that's basically it.